Hi, my name is Jagdeep Bhatia, and my research was in machine learning, specifically a subfield of that called interactive learning, where I designed and analyzed data-efficient machine learning algorithms. And I think this kind of research is important because it's really what's going to allow us to create fully autonomous robots in the future. So let's start with an example. Let's say we're trying to train a machine to classify foods as healthy or unhealthy. How would we go about doing that today? Well, we give the machine a whole bunch of labeled training data up front. So for example, apples are healthy, donuts are unhealthy, carrots are healthy, and so on. And then we'd let the machine generalize to other types of foods. However, there's a problem with this traditional non-interactive approach, and that's that often we don't have a lot of training data up front, or sometimes these machine learning algorithms need to be used while they're being trained. And so this is why we need interactive learning, where a learner learns by asking questions and receiving feedback from a teacher. So for example, an interactive teacher could tell an interactive learner, hey, apples are classified as healthy, whereas you classified them as unhealthy. And this was the core principle behind the learning from random counterexamples model that I studied in my research. This model was proposed by Professor Engelman and Tyler Dorn at Yale, and they also proposed an optimal max-min algorithm within this model. However, I had three questions about their research. First, could I simplify their work? Second, could I solve their open problem? And third, could I bound the worst case performance of learning in this model? So to answer the first question, I designed the majority learning algorithm. Here, the learner learns by learning a classifier from their set of classifiers. And in every round, they pick the classifier based on what they think is the most likely classification of each of the foods. So not only is this a more natural algorithm compared to the max-min algorithm, but I was able to show that the learner can eliminate, by following this procedure, the learner can eliminate a quarter of their classifiers from this set in every round. And therefore we can conclude that they learn in the optimal amount of time, which solves the first question. So for the second question, I designed a randomized learning algorithm to solve the open problem. I showed that if the learner picks from a specific probability distribution, they pick their classifier from a specific probability distribution, then they can also learn in the optimal amount of time. And I designed the specific distribution to be the teacher's probability distribution from which they pick the correct classifier, updated in each round with the help of Bayes' theorem. And this solved the open problem. And finally, I showed that any interactive learning algorithm, not just ones following the majority or randomized learning algorithms, can perform at least as well as their non-interactive counterparts in the pack learning model. So these are three theoretical results, but how do these algorithms actually perform in practice? Well, in my simulations, I found that the majority learning algorithm actually outperforms its theoretical bound. And the arbitrary interactive learning algorithm actually significantly outperforms its non-interactive counterpart. So what do these results tell us? Well, they allow us to compare interactive learning and non-interactive learning. We see that when the interactive learner is cooperative, then they outperform their non-interactive counterparts. And even in the worst case of this interactive learning model, the interactive learner, according to the theoretical result, performs at least as well as that non-interactive learner. And according to the simulation result, they actually outperform that non-interactive learner. So I think this research really shows the power and the potential of interactive learning. And in the future, we can probably see these algorithms in a surgical robot adapting to an individual person's anatomy, or in a factory robot working where a robot learns to work alongside a human by learning their habits and patterns. But going beyond that, I think the mathematical techniques used in this research, specifically the design and analysis of algorithms, has the potential to solve some of the other pressing problems in machine learning. Specifically, that machine learning is not interpretable, it's not accumulative, and that some of the models that these algorithms produce often have bias and discrimination.